In the last segment, we've seen 3D linearized elasticity using coordinate notation in strong form. What I'd like to do to start off this segment is, for completeness, put down the direct notation version of the strong form of 3D linearized elasticity. Okay, so let's start then with linearized elasticity in 3 dimensions. Okay, direct notation. Okay, the setting is as before. We have our basis, E1, E2, E3. We have our body, right, omega. We have our position vector of a point there, right? And as we've done before, we observed that for boundary conditions, we have Dirichlet boundary conditions for each spatial dimension, right? So this is where we have u sub I equals u g sub I for a specific I, right? And in the complementary part, we have the traction boundary condition, right, or the Neumann boundary condition for a specific I. Okay, and remember that the whole business with the fact that we are now looking at a vector problem, right? Our solution, the solution that we're looking for is a vector solution with 3 components. This is what specifies that when we look at the boundary of the body, we need to specify boundary conditions separately for each component. So it being linearized elasticity being an elliptic problem, it means that we do need to have boundary conditions at every point of the boundary. But what can happen is that perhaps over the maze part of this boundary, we specify maybe the U1 component of the displacement. Over the blue part of the boundary, which is complement to the maze part, we may be specifying therefore the T1 component of the traction. All right. However, over a different part, maybe this part of the boundary, we specify the U2 component of the displacement, and on its complement, which is facing me, we specify the T2 component of the traction. Observe that the way we've partitioned the boundary for the 2 different cases, for spatial dimension 1 and 2, are overlapping, right? Okay. And likewise for spatial dimension 3, it may be a completely different sort of partitioning. Okay, however, the partitioning for each spatial dimension must satisfy the requirement that the Neumann and Dirichlet boundaries are disjoint. Okay, as I've indicated in the figure here. Okay, so we have, of course, that that the boundary is equal to the Dirichlet boundary union the traction bound, the Neumann boundary, and furthermore, for each such decomposition, the intersection is disjoint. Right? Sorry, the intersection is empty. Right? Those boundary subsets are disjoint. Okay, given all this, here's what we want to do. What we want to say is, given UG sub I, T bar sub I, the vector f, now I'm using direct notation for the vector f, okay? And the constitutive relation sigma equals C contracted with epsilon. Note that I'm using direct notation here for the contraction of the fourth order tensor C and the strain tensor epsilon. Okay, given all this and the kinematic condition, the kinematic relation epsilon equals the symmetric part of the gradient of u. Okay, given all of this, find u, okay, such that okay, we have divergence of sigma plus f equals a zero vector in omega. Okay, and then we also have u sub I equals ug sub I on that Dirichlet boundary. Okay. Note that we cannot write out the Dirichlet boundary condition in direct notation simply because the boundary subsets are different and each component is specified possibly on a different boundary subset, right? And the same thing happens for the traction condition. For the traction condition, we can, however, write sigma n, which is a vector. We're saying that its ith component equals t bar I on partial omega t bar I. Okay, right. One thing to note here is that this notation del dot sigma is sometimes written as divergence of sigma, right? And it is sometimes also interpreted as taking this operator, the gradient operator, and dotting it with sigma, okay, which is also the same thing that's expressed here. Okay, all right. This is it then as far as direct notation is concerned. Perhaps the one other thing to remember is that when we write in direct notation C contracted with epsilon, this is a second order tensor. Okay, this is a second order tensor with free indices ij. Okay, and this is by definition, this is C I j k l epsilon k l. Okay. All right, so this is direct notation. This is an explanation of direct notation using coordinate notation. All right. Now, however, in order to develop our formulation, I'm going to prefer to use coordinate notation because it makes all the manipulation of indices much more transparent. Right. Long before we get into that, however, we need to say a little more about the constitutive relations. Okay, so let's do that. We have sigma, I'll use coordinate notation now. Sigma ij equals C ij kl epsilon kl. Okay, let's say a few things about this. C ij kl is a fourth order tensor. It's called the fourth order elasticity tensor. Okay. For linearized elasticity, it is constant with respect to, WRT is short for with respect to, right?Cijkl is constant with respect to epsilon, right? With respect to the epsilon tensor, right? So this is what we mean by linearized elasticity. In the context of linearized elasticity, this is what we get. Essentially what that means is that the relation between sigma and epsilon is a linear one. Okay? The relation on this, in this equation, is a linear one when we have linearized elasticity, and that is translated by the fact that C is a constant with respect to epsilon. Okay. I want to say a few more things about the properties of C. C has what we call as major symmetry. Okay? And it's important that we understand these properties because we are going to use them when we develop our formulation. Okay, major symmetry. What this means is that C ij kl equals C kl ij. Okay, and here's why. It follows from the fact that when one is dealing with linearized elasticity, linearized elasticity itself is built upon the idea that there exists a function that backward-looking E is the symbol for there exists. Okay? There exists a function psi, okay, which is a mapping from S3, S3 being the space of symmetric second-order tensors. Okay? There's a mapping from that space S3 to the space of positive reals. Okay? All right? So S3 is symmetric second order tensors. It's that space. Okay. Now, there exists a function psi which is mapping from S3 to R. It's in fact written as psi function of epsilon. Okay, and this is the strain energy density function. Right? We saw an explicit form of strain energy density function when we developed our variational methods for linear elasticity in 1D. Right? We considered a quadratic form there. We'll get into the particular form for psi in a little bit, but let's just, for now, all we need to know is that this exists. Okay? It can be shown then that right, one can show that C ij kl is the second derivative of psi with respect to epsilon ij and epsilon kl. Okay? In fact, linearized elasticity, since it says that C is a constant, also says that since C is constant with respect to epsilon, okay, it implies that psi is at most what? In fact, psi has to have a certain form. Can you think of it? Psi of epsilon is quadratic. Okay, so this second derivative of psi with respect to epsilon can be taken, and in general it's non-zero. Okay, because Cij_KL has that relation to the second derivative of psi with respect to epsilon, it follows that Cij_KL, which is equal to second derivative of psi with respect to epsilon ij epsilon KL, is also second derivative of psi with respect to epsilon KL epsilon ij. What condition do we need to have that to be true? It is that in general psi is, let's just say here, smooth enough, okay, with respect to epsilon. It can be made more precise, but for our purposes, that's all we need to do. All right, if psi is smooth enough, we can interchange the order of derivatives of epsilon ij and epsilon KL, right? But then, if you look at the second, or rather the third member of this equation, this by definition is just C KL ij, right? And what we've called our major symmetry has just been proven. Okay, so the fact that C has major symmetry really follows from the existence of the strain energy function, strain energy density function, right? It emerges, however, that C has further symmetries, okay? C also has minor symmetries. Okay, which is that C ij KL equals C ji KL. Okay, and this follows because the stress is symmetric. Okay, it turns out that the stress that we are dealing with here is properly called the Cauchy stress, but actually that's a detail that is somewhat lost in the context of linearized elasticity. Okay, it gets more important if we were doing nonlinear elasticity, which we are not. Anyway, the Cauchy stress is symmetric. Okay, which is that sigma ij equals sigma ji. Can you think of why that last relation holds? It follows from the balance of angular momentum for this version of the theory of elasticity. Okay, well, if that is the case, what we have is sigma ij, which from our constitutive relation is Cij KL epsilon KL, and note that the KL indices are being contracted out with the KL indices of epsilon, leaving free indices ij. Okay, but this is also sigma ji, which from definition is C ji KL epsilon KL. Okay, these two conditions then imply that Cij KL equals C JIKL, right, which is this condition of minor symmetry that we'd put forth. Okay? C has the other kind of minor symmetry as well. Okay, so the other kind of minor symmetry is that C IJ KL equals C IJ LK. Okay? And why does this come about? This comes about because epsilon KL is 1/2 by definition. It's 1/2 U K comma L plus U L comma K. Right, and remember what that is? That is just 1/2 derivative of UK with respect to XL, which is the first term in the parenthesis, plus derivative of UL with respect to XK. Okay? Well, if this is the case, it follows that epsilon KL equals epsilon LK. Okay? But then what that says is that sigma IJ, which is C IJ KL epsilon KL, is also C IJ KL epsilon LK. Right? Okay? Now, if you look at the order of the indices here, because of this contraction, right? Okay, and recognizing that L and K are just dummy indices, okay, it follows that this last term can equally be written as C IJ, okay, LK epsilon KL. All I've done there is to switch the order of to switch the position of the K and L indices. Okay, it doesn't matter because they're dummy indices and they're being contracted out anyway. But then if you compare this and that, okay, it implies that C IJ KL equals C IJ LK, okay, which is what we had set out to prove for the second of our minor symmetries, right, this one. Okay, that sort of sums up what we needed to say about the symmetries of our elasticity tensor C. We will use these symmetries in a very important way when we develop our formulations for finite elements. All right, we'll end the segment here.